sir with us today and share his insights in brachytherapy. So, sir, please.
Oh, thank you, Dr. C.P. Bhatt, Dr. Nias, and Dr. Arvind Sukla, and other colleagues as well for inviting me for this lecture. I'm really thankful for this opportunity, and I will try to have some interactive lecture rather than one-sided lecture from my side. So I will just take a minute for sharing the slide.
കേൾക്കുന്നോ ക്ലാസ് ബ്രാക്കിതെറാപ്പി കോൾപൂർ കേക്ക് കുറച്ചും കൂടി
Just a minute.
കണ്ട ഞാൻ എത്ര നാളെ കുഞ്ഞിട്ടുണ്ടെടുത്തേ
So I hope my slide is visible now.
Yes, sir.
Yes, sir.
Okay. Fine. So good evening, everyone. I will be talking on new code of practice for calibration and dosimetry of brachytherapy sources. So now to start with, when we talk about the calibration of brachytherapy source, we always like to look for the method, procedure, instruments, quantity. So, and we were doing the work in our own way. For example, we used to use one kind of detector, other used to have another kind of detector. So just to have some kind of harmonization, IAEA introduced some technical guidelines through a publication which is called TechDoc 1274, and the title of this publication is Calibration of Photon and Beta Ray Sources Used in Brachytherapy. So what guidance they provided here, they have provided the quantity, in which quantity the strength of a brachytherapy sources should be mentioned. So they zeroed to reference air karma rate or air karma strength. Both are acceptable. Method for measurement of the source also prescribed. They have recommended the use of ion chamber. Now it is the choice of the user, whether the user like to use bell type ionization chamber or a cylindrical ionization chamber, because the method depends on the use of a detector. So both of these approaches were acceptable by this guiding document. However, the one drawback, what was missing from this guiding document is they have not provided a calibration procedure for cobalt-60 source, because now cobalt-60 source is becoming a popular SDR brachytherapy source. So these are some of the limitations and disadvantages of IATEC 1274, which was introduced in the year 2002 to eliminate these limitations. It was required to have some different approach which has come forward or which has been brought in by IA. So I will come there. So now what instruments we were using in the past, say for example, if I have to measure a strength of a cesium-137 tube source, which was used for the gynec brachytherapy, or iridium-192 Bayer source or seed source, or iodine-125 seed source, or even palladium-103 seed source, then usually we feel bell type ion chamber is a handy instrument. It can be used in a reproducible manner, and so that you can see the consistency of measurement as well. Even bell type ion chamber was a good instrument to be used with high dose rate brachytherapy sources like iridium-192 and cobalt-60. But the TechDoc 1274 has not provided method for cobalt-60. Similarly, when a unified approach was not available, many of us were familiar with using a cylindrical ionization chamber, which is used for output measurement in teletherapy. And the measurement method could be either placing the detector and the source in air with the help of some rigid placement device, that is a specified jig, or one can even go for in phantom measurement. But when one was aiming for in phantom measurement, Ideally, SDR sources thought to be suitable. So the reason is for LDR sources, the signal strength was so small that it was not possible to do in phantom measurement and go for calibration of source. So to eliminate this limitation and to have some relevance or convergence with the existing code of practice for teletherapy, IAA formed a task group, and they have also included some stakeholders from APM, JEC, ISTRO, and the task group took considerable time for bringing a recommendation in terms of technical report series number 492. And the title of this report series is Dosimetry in Brachytherapy and International Code of Practice for Secondary Standard Laboratories and Hospitals. It is just like the same whatever we have seen in the case of TRS 398. So they thought that the methodology, the description of the method, instruments, calculation approaches, they tried to have some resemblance with the existing TRS 398 as well. So this new development prescribes standards, dosimetry standards, also recommends what type of detector should be used and which type of source. They have also provided some input about the existing technologies of brachytherapy and what should be the dosimetry approach when the question comes for the patient dose calculation. So in summary, TRS 492 prescribes an approach for calibration of brachytherapy sources, recommending the use of a reentrant type bell type ionization chamber and recommends the use of APM TG43 dosimetry formalism. 43 you means this updated dosimetry formalism which was published in Medical Physics by Rivardita. Now, so if we want to see case by case where these recommendations are applicable and where they are not applicable. For example, these recommendations of TRS 492 are applicable in case of cobalt-60 and iridium-192 high dose rate and high energy brachytherapy sources. This is also applicable for calibration and dosimetry of palladium-103, which is a low energy gamma emitter, iodine-125, which is also a low energy gamma emitter, cesium-137, which is also a low energy gamma emitter. Here also we can use these recommendations provided by IAEA. These sources, palladium, iodine, and cesium-131 are classified as low energy brachytherapy sources, and majorly they are used for permanent implants or in some cases temporary implants also. Now they have also provided recommendation for measuring the strength of strontium 90 intravascular brachytherapy source. But for your information, intravascular brachytherapy is not so popular now. It was in use for decades ago. However, some of the institutions in the world might be using. That's why these recommendations are available here. Please take a note. These recommendations are not applicable for beta emitting eye plaques and applicators like ruthenium 106 eye plaques are very commonly used for managing ocular cancer cases. So this approach has not yet been provided. Stranded seeds and mesh type sources which are used for interstitial brachytherapy, miniature X-ray source which is used as a source for even gynec brachytherapy and other brachytherapy applications, popularly known as electronic brachytherapy device, and it emits X-ray of energy about 50 kV. Sources used in targeted radionuclide therapy like iodine-131 for thyroid cancer and similarly lutetium-177 for other applications for therapeutic purposes. So these are the areas where these recommendations are not applicable. What I mean to say, these are the area which is out of scope of the recommendations of IAEA TRS 492. The specification and method for assessment of preference class bell type ion chamber has also been provided in this report. Test parameters and tolerance for commissioning of the bell type chamber system is also provided. So what this report requires from a hospital medical physicist, whenever you like to purchase a bell type ionization chamber for the purpose of calibration and dosimetry, you need not accept it blindly, whatever manufacturer says you. Rather, you should test this instrument against a given specification and given performance parameters. So these informations are also available or the part of the IAA TRS 492. Now, as I said, these recommendations are based on standards of air karma rate. Now, the question is, what is the standard of air karma rate? So, air karma rate, we know that if we are using photon emitting brachytherapy sources, they transfer their energy to the medium, to the air, and they generate secondary electrons. But if in case of karma, we hardly think of what has happened to the energy transferred to a given point of the medium. So we need to fabricate or design a radiological standards, mainly ionometric standards, which can work as a reference or at least reference standard for calibrating the bell type chamber of the hospital. So one of the reference standard which we have developed at BARC is a cylindrical graphite ionization chamber. It is having the sensitive volume of about 1000 cc and other parameters like it is made from 1.76 gram per cc graphite, which is called high density graphite. Then wall thickness is about 4 millimeter. Outer diameter of this cylindrical chamber is about 10.8 centimeter, and height is 13.6 centimeter, which you can see in this figure. This is the homogeneous graphite cylindrical chamber, which is used as a reference standard for calibration of hospital bell type chamber or hospital chambers used in brachytherapy by our standards laboratory also. And in this chamber has been tested against theoretical calculations. Even the calibration coefficient of this chamber in terms of air karma rate was evaluated using analytical method, and it was found that all the approaches are giving the same value, and the characterization results indicated that this chamber meets the criteria whatever prescribed by IAA in its report TRS 374 as a reference standard. This is another reference standard, which is once again a cylindrical ionization chamber for cobalt 60 SDR brachytherapy source, and one more in a spherical geometry, once again for SDR brachytherapy source. So what I mean to say, when TRS 492 came as a recommendation for using at hospital for measuring the source strength of brachytherapy sources, we were well equipped from the radiological standard point of view that if we need to implement it in practice, definitely we are ready and we can implement it. Now coming back to the recommendations of TRS 492, this report recommends the use of a reentrant type bell type ionization chamber. I hope all of you understand reentrant. This is there is a venting arrangement in the chamber. This is the schematic drawing which I have taken from the report itself. Now you can see here this is the chamber housing. This is the outer electrode. This is the source which is positioned inside a tissue equivalent jig. Then there is a vented air volume. Then there is a guard ring. Then high voltage supply, and when high voltage insulators are there. So this design is just like a design of any other ionization chamber, except it is having a bell where you can position a detector and you can measure the response of the different locations of the bell. So this chamber is recommended for measuring either air karma strength or reference air karma rate from the brachytherapy sources. My discussion will be mainly focused on high dose rate brachytherapy sources, even though LDR brachytherapy sources can also be dealt in with a similar approach. But for example, I will be taking the case of high dose rate brachytherapy source because this is a more popular choice for almost all the institutions. So this is the bell type chamber is a vented bell type chamber designed for brachytherapy application, and this type of chambers are available from multiple vendors. I will show you some of the chamber which is available in the market. A removable source holder, usually it is made from PMMA, that is plexiglass also it is called, or in some case for low energy brachytherapy sources, metallic position, these holders are also available. For example, aluminum holders are available for a standard imaging 1000 bell type chamber for iodine 125 sheet source, which we are having at BARC. An electrometer of suitable current range is required for using this bell type chamber. The report recommends the electrometer should be able to measure the current in the range of femtoampere to about 200 nanoampere. Extension cable, which is usually a triaxial cable, which is usually a low noise cable with triaxial connectors are required for use with this detector. Now, what is the requirement of a reference class bell type chamber? This is prescribed in the new code of practice, that is TRS 492. They have specified that sensitive volume should be unsealed, unpressurized, open to atmosphere. Many times you can see that pressurized bell type ion chambers are also available, but those bell type chambers are not recommended here. Bell size having a depth of about 30 millimeter, depth of about 100 millimeter and diameter of about 30 millimeter. This is nominal. It is not a strict requirement. Leakage current, definitely it should be less than 0.1% of the leakage current obtainable from the sensitivity of the detector, and with source, and without source it should be less than or equal to 50 femtoampere. Length of the sweet spot. I hope all of you are aware, whenever you go and find out the response or sensitivity of the different points inside the bell, one of the points or a group of points in the close vicinity are thought giving highest response. So those region or those spots are called sweet spot. So usually we have to scan the whole bell and find out the position of sweet spot. It is recommended by this report that this length of the sweet spot should not be less than 30 millimeter, because it will have, if this is very narrow, then it will enhance the uncertainty because of the position of the source. And ideally, this length shall extend up to 50 millimeter. Ion recombination, that is saturation correction, shall be less than 0.2%. Polarity correction, if operated at the polarity which is used for calibrating this instrument by a standard laboratory, shall not be required. Signal magnitude, usually if you are having a bell type ion chamber of nominal volume about 200 cc, the signal strength will be ranging from 200 picoampere to 200 nanoampere, and the resolution the report required shall be within 0.1%. Energy response of this detector shall be insignificant for thin wall bell type chamber, but some of the bell type chambers are also thick wall bell type chamber, just to have energy discrimination. So if this is the case, then you need to quantify the energy response of this bell type chamber. Environmental sensitivity, that it should be less than 0.3% for the relative humidity in the range of 15% to 80%, whatever we follow for calibration of dosimeter also. Short-term reproducibility shall be less than 0.1% after a stabilization time of about 30 minutes and more. And long-term stability for a period of 2 years shall be also less than 0.2%. Holders, as usual, whatever be the size of the source, accordingly we have to design or make a holder or purchase a holder from the market. So these are the requirements prescribed by IA TRS 492 to classifying a bell type chamber as a reference class bell type chamber. Now you can see from the example, this is also given in the TRS 492. We are having bell type ionization chamber from a standard imaging, that is one for intravascular brachytherapy, that is called IVB 1000. Another is for high dose rate brachytherapy, that is called 1000 plus. Then we have from PTW, the make of this code of the detector is 33005. And another which is PTW 33004. This is also called as SDS chamber, which was supplied along with the supply of remote after loaded by nucleotron. Now it is Electra. So now you can compare all these parameters. There are some minor variation here or there, but these four chambers can be classified as a reference class bell type ionization chamber, and they can be used for measurement calibration of brachytherapy sources, whether SDR source or intravascular source, or even low energy, low activity sources also, which are used for interstitial brachytherapy. Now, what is the requirement for commissioning a bell type chamber? Once we are sure that bell type chamber is meeting the specification of TRS 492, whether we need to do some tests. So yes, the answer is yes. IAEA has given many tests. For example, one test they say mechanical integrity. So what they require you to check, have a visual check of this detector, and also take a radiograph of this detector to see whether this detector has suffered any damage while transported from the manufacturer or supplier side to your side, or there is any loose cable connections available to this detector. So tolerance provided here is ideally there should not be any damage, there should not be any loose connection, and the venting hole should be very clear to allow the exchange of the air from the environment. Leakage current, it should be less than 0.1% for high dose rate or pulse dose rate sources, and it should be less than 1% for low dose rate sources. Sweet spot length, as I discussed earlier, it should be at least of the order of about 30 millimeter for all types of sources, and recombination shall be less than 0.2%. And these all needs to be measured by the user whenever they receive the bell type chamber. Polarity effect usually not required to be measured, because if you are using the same polarity for measurement, whatever has been used by a standard laboratory, short-term repeatability or reproducibility, as I stated earlier, it should be less than 0.1% for HDR and PDR source, and less than 1% for LDR source. So whenever you receive a bell type ionization chamber, you are having a remote after loading brachytherapy source, or maybe having some seed sources for use in permanent or interstitial application. So you can use this source for testing these parameters and satisfying yourself that it is meeting these requirements. Now coming to the use of this detector in the source strength measurement. So before that, as I said in the beginning, IAEA Tech Doc 1274 has prescribed the use of a quantity which is called reference air karma rate, and APM TG43 has recommended a quantity which is called air karma strength. So now in this report, reference air karma rate is quoted as capital K dot delta R. Delta is the cutoff energy above which this quantity is defined, and cutoff energy for low energy sources is about 5 kV, and high energy sources is about 10 kV. Now the question is, what I mean to say by low energy and high energy? If the energy of the source, energy emitted, energy of the photon emitted by the source is less than 50 kV, it is classified as low energy brachytherapy source. But if energy emitted by the source is more than 50 kV, then it is called high energy brachytherapy source. So accordingly, you have to have the value of delta, that is cutoff energy for air karma rate measurement or air karma strength measurement. As per ICRU definition, RAKR is defined as the air karma rate due to photons of energy greater than a cutoff value of delta of about 5 or 10 kV at a reference distance DR of 1 meter from the source center along its transverse bisector in vacuum. Now this definition is given in vacuum. So what I mean to see, practically we might be using this detector in air. So if we have to satisfy the requirement of this definition, either I should be applying a in air scatter correction factor, or if we are using a bell type ionization chamber, the bell type ionization chamber shall have outer shielding to minimize the contribution of the scatter in air scatter. So this can be achieved in either way. For air karma strength measurement also, this definition is given in vacuum, that is correction may be required or it can be eliminated by means of the design of the bell type ionization chamber. And air karma strength is defined as air karma rate multiplied by distance square. So if somebody say, for example, I measure reference air karma rate and I am interested of knowing what should be the air karma strength of this source. So you can see from this expression, reference air karma rate is equal to the air karma strength multiplied by inverse square factor. So what I mean to say, air karma strength is defined at any distance from the source, but ideally we take a distance of the from the source which is 10 times of the largest dimension of the source. For example, if I am dealing with iridium 192 SDR source which is having a length of about 5 millimeter, then I will definitely like to have a measurement distance of air karma strength of about 10 multiplied by 0.5 centimeter. So it is about 5 centimeter. So this is this way you can use this source as a point source. Otherwise, it will not be behaving like a point source. So if you apply this inverse square correction factor, you can convert from measured air karma strength to reference air karma rate, or vice versa is also true. Now for the calculation of source strength, air karma rate at a given time t and at a reference point by a reference source model SM0. Source model SM0 is that model of the source which is available at the calibration laboratory, that is a standard laboratory. So they are using this source for calibrating your dosimeter. So this can be given by this expression. The air karma rate or air karma strength is equal to the calibration coefficient against that source in terms of either air karma rate or air karma strength multiplied by the corrected meter reading at a given time. So if this is the case, we will be able to calculate the source strength in terms of either reference air karma rate or air karma strength. When the measurement is done with a different source model, because it may not be true that whatever source is available at a standard laboratory, the same source is available at the user site or the hospital. In that case, this report has recommended the use of a source model correction factor, which is in line with the beam quality correction factor recommended in TRS 398. And there is a table given by this report that what is the source model correction factor if a particular source is used as a reference source and other source is used as a test source of the hospital. So with source, now you know that if, for example, we are dealing with iridium 192, there will be a decay correction factor because iridium 192 half-life is around 73.9 days. So definitely, if you like to have improved accuracy in measurement of the source strength, definitely this correction should be applied. So the reference at a given reference time, this reference time sometimes I will tell you, for example, if we are calibrating an instrument and our environmental condition of the calibration room is 22 degrees Celsius or 24 degrees Celsius, we do not force the cooling system to maintain the temperature. Rather, we do the measurement at the given temperature. And then after calculation, we project this measurement at the standard temperature and pressure, whatever is recommended for quoting the calibration coefficient. So in the same manner, if we are calculating the source strength at a given reference time, it could not be possible that whenever we have measured, we are quoting this. I could have done the measurement at 10 o'clock, but my calculation might have been over by 4 p.m. So I could express the source strength at 4 p.m. also. This is possible by applying the required projections. So if I need to calculate the source strength at a given reference time and the data has been taken at a measurement time t measure, And this is the calibration coefficient. It could be in terms of RAKR or it could be in terms of AKS given by the standard laboratory. Then source decay correction factor and source model correction factors are required for calculating this source sustain. This source decay correction factor is nothing but a standard relation. We know that activity at time t will be equal to activity at 0 time or reference time multiplied by exponential minus lambda t. So same expression is used here also. Secondly, meter reading is the corrected meter reading. So it incorporates the correction, varieties of correction factors, which I will tell you in the subsequent discussion. Now, what is the reference condition for measurement of the source sustain recommended by this report? So this report says that reference condition is nothing but a set of values of influence quantities like you maintain a given ambient temperature of so and so, pressure so and so, relative humidity in so and so, radiation quality emitted by the source you need to know, geometrical arrangement of the source with respect to detector you should have in such a manner that in-air scatter is minimal or insignificant. So if you are satisfying this condition, then it is called that you are doing the measurement under reference condition. Like we have reference conditions in case of external beam therapy output measurement. So these are the different source model. Say for example, if the standard laboratory is having one of these iridium-192 source, but hospital might be using remaining 4 source models of iridium-192, then in that case, source model correction factor is required. So I have a table taken from the TRS 492, which gives indication that what should be the magnitude of the source sustain source model correction factor. Now for dosimetry of the source, this is for patient dosimetry. Usually you are aware that we require dose rate to water or dose rate to tissue. This is our requirement. In addition, some of the standards laboratories are also providing calibration of the instruments in terms of absorbed dose to water. So if this is the case, then the source sustain can be quoted in terms of absorbed dose to water also. And here the expression, calculation expression is remains same. One difference we have that now we require the calibration coefficient in terms of absorbed dose to water for the given model of the source, and rest of the parameters are remain same. Sorry. So after all this, now we are able to calculate when we have positioned the source in the bell chamber. You have made all the connections, you maintain the temperature, pressure, or you have the arrangement for recording of temperature and pressure. Then you can proceed for collecting the meter reading with a spot position of the source. So some experimental value and data I will show you later. So once you are finished with all those, then you can calculate the air karma rate if your detector is calculated in terms of reference air karma rate for a given source. Or if you are interested of knowing the air karma strength, then you should use a detector which is having calibration in terms of air karma strength for a given source model. All other parameters, whatever we discussed, are the correction factors to the meter reading. Now, what the code of practice is showing or stating, measurement place, this says that a shielded air conditioned room, instrument used, reference class, reentrant, bell type chamber, whatever we discussed so far. Measurement environment, it should be such that it does not require correction for room scatter or in-air scatter. Bell chamber support should be provided on a low-Z material table, or it should be table made from plastic, wood, or a stable foam, so that these materials does not give significant scatter contribution. It needs additional correction. Location of the bell chamber, ideally 1 meter away from all the walls, ceiling, floor, and remote after loading brachytherapy unit also. Relative humidity shall be in the range of 20 to 70%. variation in air temperature shall be within 0.5 degree per hour, means it should be having a stable temperature condition. Whatever your air conditioners are available, it should give a stable temperature within variation of 0.5 degrees Celsius per hour. A stabilization and equilibrium time for bell chamber and its source holder is also required, because unless the instrument is fully warmed up, you may not expect a stable reading. For that purpose, it is recommended that you put your bell chamber in the same room where you are going to do the measurement, and put the electrometer at least half an hour before, so that you are taking the reading from a stable condition of the instrument. Now this is a practical situation. I am taking an example of measuring the source strength of SDR iridium 192 brachytherapy source. Now you see, this is the SDS chamber supplied by the manufacturer of the supplied by the supplier of the remote after loading brachytherapy unit. Now you can see we have positioned this detector over the foam sheets, and here these are the plastic sheets, so that room scatter or in air scatters are almost negligibly small. Now you can see distance of this detector is almost 1 meter or more than 1 meter away from all the balls, including distance from the remote after loading unit is also approximately 1 meter. Now once your bell type chamber is positioned this manner, now you need to find out what is the sweet spot. For this purpose, usually we select around 10 to 15 dual positions inside the detector and go on taking the reading at every dual position number, maybe some 95 mm down from the top of the bell, then 90 mm, 85 mm, 80 mm, something like. So go on taking the source up and taking the reading at an interval of maybe about 5 mm. Then you will need to plot a curve. So this curve will be giving you bell response. So these are the bell response also quoted in the report IATRS 492 or PTW 3305 bell type chamber, PTW 3304 and SDR 1000 plus. You can see bell response is also almost looking similar. However, for standard imaging intravascular brachytherapy bell chamber, the bell response looks to be somewhat different, because so here, even though this measurement is not so popular nowadays, but this is for your information. So here you have to select one of the point as the sweet position. So one of the dual position will be selected at a sweet position. Ideally, it should be within the in the center of the whole uniform region. So once you are decided about the dual position, then you can repeat the measurement, note down the meter reading, and after meter reading, also record the temperature and pressure, then leakage leakage from the remote after loading brachytherapy unit. If electrometer is calibrated separately, then electrometer calibration factor, polarity correction factor. If you are using the same polarity, then it is 1. But if you are using a different polarity, whatever used by a standard lab, then it should have some value. And then recombination correction or saturation correction factor, that is case. One more correction factor you can see here, K altitude. This is called, particularly for low energy brachytherapy sources, it has been found that the formula given for temperature pressure correction factor by the ratio 273.15 plus T divided by 273.15 plus T0 into P0 by P is not applicable. It is not applicable for low energy brachytherapy at high altitude. Say for example, if my hospital is available in Dehradun or maybe Jammu and Kashmir, and if I am dealing with iodine 125 source or palladium 103 source, probably temperature pressure correction factor calculated using this formula is not correct. So a number of publications are available in this direction. They have recommended that the KTP calculated by this minor needs to be corrected by a parameter which is called H1 and H2. And this work has been done by many groups. So this altitude correction factors needs to be incorporated when we are dealing with low energy brachytherapy sources and at higher altitude. So once you put the values of all the correction factors and use this relation, reference error karma rate and the measured corrected meter reading, then you will be able to get the value of reference air karma rate, or if your chamber is calibrated in terms of air karma strength, you will be able to get the value of air karma strength. Now the question is from where we will get the value of SM0, that is source model correction factor. So IAEA has provided a table. This is the value of H1, H2 for finding out the correct temperature pressure correction factor using the relation K altitude is equal to H1 and T to the power H2. So values of H1 and H2 are given here. This depends on the make and model of the source. So accordingly, this value is given for palladium 103 isoid advantage, palladium 103 Siva dot, iodine 125 select seed from Theragenex, then iodine 125 of Amerson. Whatever design, the Emerson design is also similar to the BARC design of iodine 125 source. Similarly, cesium 137 source is supplied by the vendor, but when measurement is done by, sometimes this factor also depends on the instruments. So if we are using intravascular brachytherapy bell chamber, then it will have a value. If we are using high dose rate 1000 plus bell type chamber, then it will have a different value. So we have to be cautious while selecting the value of this parameter for finding out the correct temperature pressure for low energy brachytherapy sources at high altitudes. Now, this is the table given by IATRS 492 for sources. So, say for example, this is the SM0 means source model available with a standard laboratory or the calibration laboratory, and the source model available with the user. So now say for example, if I am dealing with Electra Flexi source AGR Radium 192, and if the same source is available at a standard laboratory also which has been used for calibrating our bell type chamber, then naturally the source model correction factor will be 1. However, if our source model is Flexi source iridium 192, but microselectron SDR V1 source has been used as a reference source by the calibration lab, then source model correction factor will have a value of 0.996. So accordingly, you can see the whole table. This table is available if the standard lab is using Electra Flexi source as a reference source, or Electra microselectron V1 source as the standard source, or microselectron V2 as a standard source, or baby iridium 192 as a standard source, or variant gamma med plus as a standard source. So all the available source models are given here, and accordingly which source is available to the user. So we have to look for the appropriate value of the source model correction factor. Now you can see from this table, the source model correction factor is up to about 5%. So here you can see 0.996 means correction is only 0.4%. But here if you see, this is 0.955. So this is correction factor is having a magnitude of 4.5%. So what I mean to say, this is additional correction incorporated in calculation of source strength, which was not incorporated earlier to enhance the accuracy of source strength measurement. Now, last item in this talk is, now always when we are dealing with source strength measurement or dosimetric measurement, we always like to evaluate the uncertainty. So uncertainty evaluation, this I have taken from the TRS 492 only. They have taken two scenarios. This scenario I have taken for SDR iridium 192 brachytherapy source. Scenario number 1, whatever has been recommended, everything has been followed in total. However, scenario number 2, there are some departures from the recommended reference condition. So if this is the case, for example, a step array care calibration of reference standard at PhD level. By the way, if this is the case that the calibration laboratory has got their instrument calibrated by primary standard dosimetry laboratory, then their uncertainty shall also be incorporated. Then a standard laboratory has used this instrument for calibrating your dosimeter or detector, then their uncertainty shall also be included. Finally, the user has conducted the measurement at their institution, and they have also have some uncertainty of their detectors, their method. So everything needs to be quantified. This is just for example. Please do not copy this for any specific measurement. It is a word of caution has been given in TRS 492 also. This is a typical example given for helping the user for estimating the uncertainty in measurement. So finally, you can see that if you are measuring the source strength of HDR iridium 192 brachytherapy source, the overall expanded uncertainty at the user level is coming 1.7% when you follow every step and every recommendation of IAA TRS 492. But if you are departing from these recommendations, your uncertainty of measurement can go up to 5.7%. Now the question is, when we should measure the source strength of the brachytherapy sources? Answer is very simple. Whenever you are purchasing a new source, definitely you should measure the source strength yourself and also compare it with the source certificates provided by the supplier. Usually it is expected that if you are comparing the measurement value with the source certificate for SDR sources, this value shall be matching within 3% variation, incorporating the uncertainty of measurement. For if you are doing this for low energy seed sources, the measured value and certificate value shall be within 5% within the uncertainty of measurement. So now finally, if I have to use this source for which I have measured the source strength, how it can be utilized for patient dose calculation or patient dose rate calculation or tumor dose rate calculation. So I hope we all are familiar. We are using 2D dose calculation formulas provided by APM, and this method can be used for the source strength as specified in terms of air karma strength or array care, because when you take the distance of 1 meter, both numerically these two quantities are similar. So here the TRS 492 recommends the use of a modified or updated information. Here you can see this dose rate at a polar point r theta is equal to the air karma strength measured by the user, dose rate constant either provided in literature or measured by the user, then geometry correction factor Gx. X stands here for if the source is small and your calculation distance is such that the source is looking like a point, then you can have point source approximation. But for example, if I am dealing with iridium 192 SGR brachytherapy source or cobalt 60 brachytherapy source, and if my interest is to measure the calculate the tumor dose rate at a distance of about 2 centimeter, probably this source cannot be regarded as a point source. So we have to take line source approximation. Accordingly, if I have to write a modified version of this equation, I will be writing dose rate at dr theta is equal to air karma strength Sk multiplied by dose rate constant, then ratio of GLR theta by GLR0 theta 0, GLR that is radial dose function for the line source, and anisotropy function Fr theta. If similarly, this is with if I have measured the air karma strength, if I have measured the reference air karma rate, you use this second equation. So by using these two equations, one will be able to calculate the dose rate at a point, and if you are using the treatment planning system, it will do this calculation at many points and will give you the dose distribution as well. So in summary, I think this is the complete information whatever I wanted to share with you. So in summary, what I would like to conclude for this lecture, The new code of practice, which is nothing but IATRS 492, prescribes dosimetry formalism mainly for photon emitting brachytherapy sources, whether it is low energy brachytherapy source or high energy brachytherapy source. The dosimetry formalism is analogous to IAEA TRS 398 because they have tried to make the similar recommendation, whatever we are using from last 2 decades or more, so that the user should have some consistency in using a code of practice prescribed by IAEA. Source model correction factor is a new inclusion in the source dosimetry formalism, that is source strength calculation. Earlier, we used to assume that all the sources are same, but the scenario is not the same. Say, for example, if I talk about iridium 192 source of nucleotron and iridium 192 source of Bari source, their encapsulation material is different. Their encapsulation material thickness are different. So accordingly, the filtration of radiation by these encapsulation materials or capsules are different. So naturally, there was a need for incorporating a correction factor to account for this variation in the geometry and a spectrum of the sources, which has been incorporated now because when data are available, then it has been incorporated and recommended. So the implementation of this code in practice is expected to improve the accuracy in source strength measurement and thereby the accuracy and dose delivery to the tumor. So thank you very much for your patience listening. Hello.
Yeah, thank you, sir. And there are a few questions here in chat box. So,
Okay.
may I, sir?
Yeah. Shall I stop this sharing? Right.
Yeah, sure. So, one question is, sir, what is the reason for neglecting the polarity correction factor in well-type chamber, but other small volume ion chamber are not? So, he want to ask, we are not, we are neglecting well-type polarity correction for well-type chamber, but for small volume ion chamber, we are taking that polarity correction factor.
No. I think probably they have listened it differently. I said very clearly, when you are using the polarity which has been
Yes, sir.
used by calibration laboratory, then there is no need of applying polarity correction factor. This is true even for external beam therapy also. But if I am using a different
Yes, sir.
polarity, then
Yes, sir.
polarity correction factor is required.
Yes, yes. Thank you, sir. And other question is, does the code specify procedure for cross calibration between different sources like cesium 137 or iridium 192?
No. The code, we are not so knowledgeable at this moment of time. We do not have that much data. They allow the cross calibration for the same type of radionuclide. So say, for example, if I am having a calibration against a given source model of iridium 192, I can do cross calibration with another model of iridium 192, but I cannot switch over from radionuclide iridium 192 to cobalt 60 to cesium. This is not allowed as on today. We do not have this much information in hand as of now.
Okay, sir. So another question is, how altitude affect low energy photon measurement? So can you please explain, sir?
Yes. Now I will tell you what has happened. In case of low energy photon, photoelectric effect is dominant. And secondly, you might have seen that when we were defining the reference air karma rate, I have put a value of delta. Delta is the cutoff energy. But in case of high energy sources, this cutoff energy is very, very small in comparison to energy of the gamma or X-rays emitted by the source or its encapsulation material. But in case of low energy sources, say for example, I am dealing with palladium 103. The energy is about 20 kV. So I cannot neglect 10 kV gamma rays, which was put as a cutoff energy in case of high dose brachytherapy sources. So because of this, the temperature air density correction factor, rather I will say rather than temperature pressure correction factor, because the variation in pressure while you go to the higher altitudes is not uniform, it is not linear, it is non-linear. So because of that, the KTP calculated by a standard calculation is not correct. it departs from that value. So accordingly, there are many publications. I have seen 5-6 publications from different groups. One from our Dr. Palani Selvam also. He has pointed out that when you deal with low energy sources and go to higher altitudes, maybe 1000 meter above the sea level, there is a significant departure from the calculated KTP value. So accordingly, it needs correction.
Okay, sir. So another question is how to choose well point for measurement and for finding the sweet spot.
Yes,
I think you explained
this is very
it,
simple.
but,
You just scan through the whole bill, and wherever you see, there may be 2-3 points at least, which will give you almost matching readings. So those 2-3 readings are, or 2-3 points are. So my suggestion would be, if you are having 3-4-5 points which are giving, so center of these points should be the sweet spot point.
Okay, sir. Okay, sir. So another question is why source model correction is required when all iridium 190 source emit the same energy?
No. It is not correct. When you quantify the spectra of the iridium sources, say for example, Michaelis electron, this nucleotron or electra now, they are making 3 different models of the source, and the design, mechanical design of 3 sources are not equal to each other. Since we were not having this information in hand earlier, so we were using every source as the same source. But when you analyze the spectra of these sources, you will find a different spectrum. That's why you can see, while we are quoting nominal energy of radium 192, we say it is 380 kV to 400 kV. We are not saying exactly 380 kV or 400 kV. So this 20 kV variation has already been indicated by different publications. So now by applying a source model correction factor, we are incorporating this variation in the energy spectrum because of different filtration by the different types and different thickness of encapsulation material.
Okay, sir. And as you already discussed that for different type of sources we have for iridium. So nowadays cobalt is also a frequently used source in clinical purpose. So you have any suggestions for when we are doing measurement for cobalt? Any suggestions for that, sir?
Yeah, actually, this code has indicated that they are in process of generating data for cobalt 60, but I feel there are only 2 models of cobalts are available. One from Flexi source and one from this Baby. So they are waiting for few more models to come in the market so that they can generate. But yes, the same approach, the same method is possible.
Okay, sir. There's one more question. So whether the seed point change after each calibration?
I don't think so, because it is the fixed characteristic of the detector. Calibration is a response variation. So whatever variation will take place, it will take place for the whole bell, not for a single point.
Okay. So one more question, sir. In IAA Tech Talk 1274, it is mentioned that for SDR iridium 190 source, a primary standard is not available. So what is the current status, sir?
I could not hear. Can you repeat this question once again?
Sir, in IAA Tech Doc 1274, it is mentioned that SDR iridium 192 source, the primary standard is not available. So what is the current status?
Yes, now I cannot say we are having primary standard, but we are having a reference standard. Primary standards are available for iridium 192 with many primary standards lab now. Even BIPM is having, I hope INIA of Italy, maybe Arpansa are also. Now many labs are having primary standard, but we are using our own reference standard, designed and maintained at our own laboratory.
Okay, sir. So one more question, sir. Does TRS 492 account for any heterogeneity correction in dose calculation?
No, because they have recommended the use of TG43 formalism, which does not account for heterogeneity calculation. So accordingly, this does not account for.
Okay, sir. So with this, I think we are here with all the questions. So
yes, sir.
Yeah.
Anyone want to? Okay. So with this, I think we are here with all.
Yes. Yes. Thank you. Yes. Thank you, sir.
I want to say Shukla sir?
Yes,
please.
yes. Thank you, sir, for very nice presentation. And it was a very practical and useful for everyone, every medical physicist in clinic.
Okay.
Thank you, sir, for a
Thank
very
you,
good
thank
presentation.
Thank you,
And
thank you.
For-
yes, sir. And thanks, Dr. Bhatt, for moderating the session. Thank you, Dr. Niaz, for creating the web and this Zoom link. And thanks to all participants who has participated in this presentation. Thank you very much, sir.
Thank you, thank you. All the best to all of you.
Thank you,
Yes,
sir.
sir. Thank you, sir.
Thank you all.
Okay. So, okay. So, see you later sometime. Thank you very much.
Thank you.
Yes, sir.
Thank you, sir.
Good night.
Okay, thank you. Bye. Bye.
Thank you. Bye-bye. Bye-bye.
Nice.
Recording stopped.